Hello, everyone. Welcome to Breathing Better, Learning Better webinar hosted by Engineers Ireland West Region. My name is Magda Hajdukiewicz. I'm a member of Engineers Ireland West Region Committee and also Director of Construct Innovate, Ireland's National Research Centre for Construction Technology and Innovation. In today's webinar, we have three fantastic speakers. The first one is Dr. Orla Hegarty from University College Dublin, who will be presenting under the topic of It's the Buildings, How Architecture Impacts Your Health. Our second presentation will be from Mr. Adam Collison at University of Galway, an evaluation of classroom air quality in Irish schools. And our final presentation today will be from Dr. James McGrath at Maynooth University on future classrooms, challenges and opportunities for indoor environmental quality. So after those three presentations, we will have a Q&A session. So please, if you have any questions, type them in at the bottom of the screen in the Q&A box, and we will be able to answer those at the end after the presentations. So first, I'd like to ask Orla to share her presentation, and I'll give you a little background on her. So Orla Hegarty is a registered architect and assistant professor at the School of Architecture, Planning and Environment Policy in UCD. Her particular interest in indoor air quality developed in 2020 when she started collaborating on research in disease transmission as a factor of the buildings. And she was a member of the expert group advising NPHET about ventilation and an expert witness to the Oireachtas Health Committee about COVID transmission and prevention.
Thank you very much for the invitation. I suppose what I'm bringing to this is my background in architecture and my developing interest in the whole area of how public health has influenced architecture in history and maybe where we're going wrong currently and what needs to change. So the first thing I suppose to get across to people is that we need to understand that indoor air is moving and mixing all of the time. Because we don't see indoor air, we often think of it as a vacuum or as something static. This is an image simulation from a restaurant in China in 2020, where they tracked the people here, who you can see in red, who were infected with COVID during the course of this lunch. You'll see there much more than 2 meters from the person who infected them. And it was modeled using the ventilation system and the air handling system in the building to track what the air movement would have been. And it mapped very closely with the people who were infected. So the first point I wanted to get across is that that is how air is moving. This looks a little bit like a classroom as well as a restaurant. And so the issues around air quality, air movement, infection, pollutants in classrooms is much more than about proximity. It's about the air in the entire space and how often that is filtered or refreshed. So just moving on, I suppose we were all aware in 2020 of the very poor understanding of disease transmission in classrooms. This top image here shows if people remember, we had this, hazard tape down the middle of desks with the idea that students would stay 2 meters away from each other. And in the extreme in Thailand, they had these little plastic cages to stop children sneezing on each other, when actually the classroom air was all of the same mixed air. And similarly in this image here. So it wasn't really of any benefit to anybody to be keeping a distance if you were breathing in and out the same air and infection was transmitted that way. So apart from it being not a vacuum, air is also, it's more a soup, and it's a soup that we swim in all the time. If we think about a fish tank, it maybe gives us a better idea of what we breathe and what we move around in. We all know that if you don't refresh the water in a fish tank by replacing it with clean water, or you don't filter the water to remove things that are contaminating it, that you very quickly will get a cloudy water and you'll probably get diseased fish. So we understand that because we see it visually. We can see the water becoming cloudy and dirty, but in indoor environments, we don't see that. We don't feel it, and humans are actually quite poor at perceiving that. Unless the air is maybe very warm or very humid, and we start to say it's stuffy or there are smells, we don't really perceive it. And particularly if we're in an air-conditioned environment where the humidity is being reduced and the air is being cooled, we perceive that as fresh air, and we don't think about what else is in that air. As long as we have a perception that it is cool, we think that it's fresh. So air is a mixture of lots of things. There are gases we know of, so we need oxygen for life, and we breathe in oxygen, we exhale carbon dioxide. It's also got VOCs from lots of things, and probably has got a lot worse over years of developing new materials. Building materials have changed, cleaning products have changed, people use cosmetics, the materials in furniture. All of these things have contributed to pollution and poor indoor air quality in buildings. We also have things like smoke and soot and dust and pollen that can be irritants for people, that can build up in the air. And then, of course, we have the issue with disease spread from viruses and bacteria. So this is nothing new. Buildings have been designed with the idea of adequate ventilation and fresh air and daylight for public health for a very long time. The earliest records I have found of monitoring air quality in schools is from the 1850s in American schoolhouses, when they were collecting the indoor air in glass tubes and testing it for the quantity of carbon dioxide that was in that. So this isn't new. Carbon dioxide has been used as a proxy to see how fresh the air is for a very long time, nearly 200 years now. And what that means is that if we are exhaling carbon dioxide and it is being retained in the room, it's a good indicator that the air is not fresh in the room, and it's something that's very easily measured. These are some images from Ireland in the Spanish flu and TB era. We can see that patients were being kept outside, and that the value of fresh air and daylight were considered very important for recovery and for people breathing clean air. These are apartments designed in Dublin in the 1930s, where they had balconies that were large enough for a single bed for a recovering TB patient. That's how pervasive TB was at the time, before there were antibiotics and treatments. And this bottom one is an image from school in New York during Spanish flu around 1918, 1919, when the schools were kept open, but they were moved outside. And even in very cold weather, the children attended school, and that was so that the parents could go to work and to prevent the spread of illnesses. And following Spanish flu, there was a whole wave of outdoor school movement in Europe, where children were educated outside, and a lot of that was driven by public health. So it's not new. To talk a little bit about what part of the world we live in and the climate we live in, because that influences how the buildings are designed. So this is a piece of research from the early days of spring 2020 pandemic, where they tracked the waves of the first wave of the worst of COVID. And you can see here it's in that yellow zone. So across from Seattle into New York in the northern United States, across into Europe, Ireland, UK, northern Spain, Madrid, northern Italy. It was particularly badly hit. Then across into Iran, Wuhan, China, South Korea, and Japan. And that yellow band is a particular climate zone between about 30 and 50 degrees north that had particular climate conditions at the time. That was a level which is now measured as at a temperature and humidity in which COVID has quite a long life. It can survive in those conditions quite well. The interesting thing about this band too is that it's quite a temperate climate, so it's a very densely populated part of the world because it is a temperate climate. But because we don't get extremes of too much bad winter, we don't tend to design our buildings for very cold weather. We tend to design our buildings for the temperate season from late spring until mid-late autumn, when we can naturally ventilate our buildings and they're comfortable, and therefore we tend to not design our buildings for those short winter months when we seal up the buildings, try to retain heat, and have very poor indoor air quality. And you see that talk about flu season. Flu season is just a factor of how we design and manage our buildings. And interestingly, 6 months later, when that yellow zone tipped into southern Australia, it was Melbourne that was badly hit 6 months later. Again, similar climate conditions, similar building design, similar issues, all measurable, all a factor of the environments that we live in. This is another little piece of interesting research from well, I think it was between 2020 and early 2021, early mid 2021, which tracked Ireland here when we saw the worst time for cases of COVID, which was in January 2021, again to do with environmental conditions at the time. But interesting, if you track the northern United States of America, you see very high levels in the spring and again in the heating season in the autumn. But if you look at the southern states, you see the peak in the summer months. And that is a factor of air conditioning, because we are now in a world where we use a lot of air conditioning, where we manage the humidity and temperature of air, but we recirculate a lot of air for energy saving, so that it feels fresh, but it's actually not fresh air. And it can have a lot of pollutants and a lot of pathogens in it, but we don't perceive that. So the whole issue of air conditioning is very important in this area. This is also the first airborne pandemic where we've had air conditioning. So the nature of spread has been quite different to, say, Spanish flu or TB. Air conditioning has only really been around for about 100 years and common in the last 50 years. And particularly air conditioning in vehicles, I think, is a big issue here that we're not talking about. So when I talk about the sort of climate around the world and the conditions of pandemic, the whole area of relative humidity becomes important, because we often design our buildings worrying about a high humidity risk. So we're trying to prevent high humidity over here, where we get fungus growth and all of those nasties. But we need to be careful, because if we go for low humidity, it can impact on human health. And as we are in a cold season at the moment, and we take outdoor air with high humidity, high relative humidity, and we warm it up, it becomes very dry indoor air. And that has definitely been a factor of pandemic spread, particularly in buildings like nursing homes that have low occupancy, and they don't have activities that generate a lot of humidity from people's activity in showering and cooking. So this area is regulated, but I think we need to be careful, particularly since the 1970s and the oil crisis. We have changed how we design our buildings. All of the learning from TB that happened in Ireland in schools in terms of ventilation, and particularly cross ventilation and high ceilings in school, has all sort of been forgotten over the last 50 years, because we've moved to, since the energy crisis, of trying to under design buildings. So we've made them smaller and had less engineering equipment. And you'll probably find the building with the worst indoor air conditions are probably from the 1980s, which was a reaction to that, to under engineer buildings and over occupy them for our cost savings. Our building regulations, the balance is in favour of adequate ventilation while limiting energy use. So you can see that the balance there has been, I would say, weighted in terms of energy saving rather than occupant health. And that's probably a factor of European legislation telling us what energy standards we need to have, but allowing each individual member state to dictate their own ventilation standards. So we have been leaning very heavily into air tightness rules in buildings, and not enough into public health and the reactions of that. So for people who are involved in building construction, of course, we have regulations at design and construction stage. We have natural ventilation, which is really rules of thumb, which are very dependent on weather conditions and on occupant numbers and on activity in buildings. So they are, I suppose, very loose in terms of, do they meet the need? And we also have engineering standards, which of course will depend on what standard is set, what specification, how well maintained the equipment is, and again, the level of occupancy and the activity in the building. Since 2023, we now have health and safety regulations and a code of practice for indoor air quality in all workplaces, so that means virtually everywhere except your own home is a workplace. And those regulations are mandatory. They haven't been very well publicized, but that shifts it from a construction standard here, which is what we're used to, into a monitoring here, where where workplace air quality needs to be monitored, and then you react and you remedy the situation where problems arise. So that's a different mindset, and it'll take time for people to understand that. It's unfortunate that it hasn't been very well publicized, because I think it's incredibly important. So coming to conclusion, I think we need to remember that infection is not inevitable. Infection risk in all buildings can be measured and managed and mitigated. We do not need to be in a situation that we are still in now, where we have disease spread in buildings and in vehicles through lack of people's knowledge and lack of monitoring. Public information is incredibly important in this area, because people will manage their own behaviour if they know the risks. Schools have been particularly at the front line in all of this, because they're high occupancy buildings. And as I said, throughout the last 200 years, schools have been designed with the knowledge that they are high risk environments, because children don't just come in and spend an hour in a place of worship, or don't just sit in low occupancy in an office or in a factory. They sit in high occupancy in these spaces, and they stay there for long periods of time. They also tend to be doing activities like singing and talking and shouting, which produces more pathogens into the air. So schools have always been recognised as core to community public health. There's a statistic from America that shows that in 2020-21, 70% of household infection came home with a child from school. So if you can make sure that schools have conditions of good public health and good air quality, that makes a very, very significant difference in terms of community public health and disease spread in communities. This is an image from the 1920s in France, where the whole idea of light, airiness, modern architecture, a lot of that was just a reaction to the whole era of Spanish flu, and the idea of buildings having to embrace public health, daylight, sunlight, and the idea of opening up buildings. So the architecture we're used to in the last century it came about because of that public health risk. So in conclusion, just keep an eye on the time. Really what gets measured gets managed. We need to move to an environment of having proper indoor air quality monitoring and training for people to react to those situations, whether it is to open up the building for purge ventilation, whether it is to reduce the occupancy, whether it is to make engineering changes over time, or whatever else that is. But unless we start measuring this consistently, we can't manage the situation. And I think from my own measurements and moving around the place, things are not as bad as you might think. And certainly the issues are mostly in certain times of the year when we are cold and we stop ventilating our buildings adequately. So thank you very much. That's the end of my presentation.
Thanks very much, Orla. Very interesting and great introduction to the topic. I think we talked about this a lot a couple of years ago when we had the COVID pandemic, and then the general population maybe kind of stopped discussing this, but it's really important that we continuously keep an eye on that, and you really emphasize that in your presentation. Thank you. We'll take questions at the end, but if anyone has any questions for Orla, please type it in the Q&A box at the bottom. Now we have our second speaker, Adam Collison, who is a PhD student at the Centre for Climate Pollution, for Climate and Air Pollution Studies at the University of Galway. Adam's research was granted awards from the Aerosol Society UK and Ireland, and it centres on indoor air quality in public buildings, including classrooms. A key aspect of Adam's work involves investigating how energy efficiency retrofits affect indoor air quality parameters. Adam's research aims to identify potential opportunities and challenges in building retrofits relating to indoor air quality, and to inform guidelines to enhance and safeguard occupant health and well-being. So Adam's presentation is shared there. Adam, if you want to put on your camera on as well, and go ahead whenever you're ready. Thank you.
Perfect. Good morning, everyone, or even afternoon. My name's Adam Collison. I'm a PhD student at the University of Galway, supervised by Dr. Miriam Byrne and Dr. James McGrath, and I'm working as part of the Benefit Project, which is a detailed experimental and modelling study of retrofitted and newly constructed energy efficient non-domestic buildings, and we're investigating, I guess, their ability to maintain a healthy indoor environment. And there's kind of a significant knowledge gap in this regard, particularly in Ireland at the moment. So I'm looking forward to sharing with you today some of the results from our pre-retrofit classroom air quality monitoring that we carried out over the last year and a half in classrooms nationwide. So we've all heard the saying, we are what we eat, but we are what we breathe as well. And every day we breathe about 4 times more air than food or liquid we consume. And while respiration is an essential part of living, of course, unfortunately, the same process kind of that sustains us also presents an opportunity for pollutants to kind of enter our body. And given that we spend 90% of our time indoors, where concentrations of some pollutants are often 2 to 5 times higher than what they would be outdoors, it becomes a bit more clear why indoor air quality is important. And I suppose furthermore, children who outside of the home spend a large chunk of their time within schools are among the most vulnerable cohort to the adverse effects of poor indoor air quality. Due to their greater air intake per unit weight and narrower airways, developing lungs and other organs, might make them less able to repair themselves. It becomes kind of very evident why maintaining ample air quality in classrooms is an essential thing to do. So the Benefit Project, which I work on, kind of focuses on 2 specific non-domestic building cohorts. The first group is offices and schools undergoing energy retrofits as part of the SEI Public Sector Pathfinder program. So this is my main research area, but we're also looking at newly energy efficient buildings too, so schools, offices and healthcare facilities. And I suppose why this is important is we all know there's a recognised need to reduce our carbon and greenhouse gas emissions. And the EU has introduced legally binding targets of around 30% in terms of energy efficiency by 2030. And retrofit or given that buildings are the single largest energy consumer within the EU, accounting for about 40% of total energy consumption and a similar amount of a portion of our carbon emissions, addressing this will be an important thing. But it's even like moreover, I suppose, given that in 2050, like 80% of buildings that will exist in 2050 already exist today. So retrofitting will play a major part of, achieving any of these targets. Having said that, though, I suppose the negative impacts of indoor air quality have been noted when energy measures are improperly implemented. But how do kind of deep energy retrofits influence indoor air quality? Well, they can in a number of ways. So the likes of changes to airflow rates due to air tightness measures can lead to a buildup of pollutants indoors, or a change in possible kind of indoor, relative ratios of, say, indoor-outdoor concentrations of certain pollutants and pollutant profile changes. Off-gassing from building materials can lead to buildup in volatile organic compounds, such as, the likes of formaldehyde or benzene. And then temperature and humidity changes are possible too throughout these retrofits. So you could end up with, some moisture issues or overheating risks. And already domestic studies in Ireland have found underventilation in deep energy retrofitted Irish homes. A recent study found that a very limited number of bedrooms monitored in deep energy retrofitted Irish homes would comply with limits set out in EN standards. But there is a bit of a gap in terms of non-domestic buildings and more specifically classrooms. So as I mentioned earlier, I'm only going to discuss schools and classrooms today, but we do have kind of this is only a subsection of our project. So a little bit about the schools. We selected a sample of schools which were very much representative of typical Irish classrooms. And all of these buildings were slated for retrofit. We visited about just under 10 schools across the country during the 2023-24 academic year. And our sample was kind of fairly well spread nationwide with a fairly uniform distribution between, say, urban and rural areas. We had 8 primary schools, 1 post-primary school, and the buildings ages ranged from kind of the mid-1900s right up to the early 2000s. Occupancy levels in the classrooms were typical, so about 27, 28 children with an occupant density of about 2 square meters per child, which is actually a little bit more densely occupied than some of our European counterparts. And importantly, all these classrooms, as is common in Ireland, are naturally ventilated. So that means no mechanical units. Ventilation was all through kind of passive means such as trickle vents, air bricks, wall vents, and of course window and door opening. So we're carrying out a pre-post monitoring campaign. So that allows kind of a comparative analysis between, and that enables then for us to capture the extent to which retrofit measures actually impact indoor air quality. So we use research grade equipment to capture precise kind of data on a variety or a whole host of key air quality parameters of concern over a week-long period. And on top of that, then we also use consumer grade sensors to collect year-long year-long trend data and ventilation measurements within the classrooms. And then on top of that, then we have a fairly comprehensive survey study which collects information on building ventilation and occupant characteristics and activities, along with perceived thermal comfort to further complement the data set. And again, this is done both pre and post retrofit. So we've completed our pre-retrofit monitoring campaign and our post retrofit's ongoing. So I'll share some of that pre-retrofit data shortly. So we measured quite a lot. And I think the first thing people think about when you talk about classroom air quality is a CO2 monitor. And I think the consensus at the minute is if you slap up a CO2 monitor, you can kind of call it a day. But the reality of classroom air quality is a bit more nuanced. And yes, CO2 and carbon dioxide is a useful indicator for ventilation effectiveness. And it can serve as a proxy for human generated aerosols, but itself isn't actually a pollutant, and we shouldn't really fixate on the readings of carbon dioxide readings as a proxy for good overall air quality. So our study took a broader approach by measuring several key pollutants, and I'll just run through some of the kind of more critical ones very quickly. So firstly, we monitored indoor particulate matter, airborne particulate matter of 2.5 microns or smaller, so PM 2.5. These particles are tiny and they can get deep into our respiratory system and bloodstream, causing a whole host of health issues. And they come from a whole pile of sources, both indoor sources and outdoor sources. So the likes of indoor sources might be something like cooking or candle lighting, or if you had a stove or an open fireplace within a home. But of course, they wouldn't be too common in the classroom environment. And more problematic in the classroom environment is ingress of outdoor sources, such as vehicle emissions or solid fuel burning exhaust, say from chimneys and whatnot. And also then the resuspension of settled particles within classrooms from, say, carpeted floors. Nitrogen dioxide is another kind of big pollutant of concern, and again, it primarily comes from vehicle emissions, but has been found at concerning levels in classrooms in previous studies, and is also known to cause a plethora of health issues. Formaldehyde then is another one we focus in on, and that's because it's commonly reported in schools, and it's an indoor kind of source, or sources are indoor really. So a lot of wood-based products, glues, varnishes, printing materials would all emit formaldehyde, but it can also be formed in the air through chemical reactions involving terpenes like limonene and pinene, which are commonly found in cleaning products that are often used in classrooms. And importantly, formaldehyde is a known carcinogen. Ozone then is another important parameter that we're monitoring, and again, it has both indoor and outdoor sources. So the likes of indoor sources would be photocopiers or printers or some air cleaners, even ironically enough, as well as outdoor sources. So ambient ozone, say, particularly in urban areas, that can be problematic. And I suppose while we measured other pollutants too, it's worth noting that the pollutants I just mentioned there, along with PM10, which is PM 2.5's bigger brother, they account for about 99% of estimated harm from like typical indoor air exposures. So it's safe to say there are certainly pollutants that should be prioritized when monitoring. So jumping into some carbon dioxide results. So in classrooms, CO2 does largely come from respiration. So it's a direct result of metabolic processes. This makes CO2 a decent proxy indicator for other occupant generated pollutants, including the respiratory aerosols that can carry viruses and bacteria. And when CO2 levels are high, it does suggest that exhaled air is accumulating and not being sufficiently diluted with fresh outdoor air. And 1,000 parts per million seems to be the number that's thrown around quite a bit when it comes to carbon dioxide. So it's a lot of the guidelines globally seem to use this as like a yardstick. And that comes from the fact that about 1,000 parts per million in a classroom of 30 students translates to somewhere around 8 to 9 liters per second per person of a ventilation rate. And interestingly enough, then from our study, we found that just under 75% of classrooms spend more than 50% of their days in excess of 1,000 parts per million. We also found strong relationships between outdoor temperature and carbon dioxide concentrations. We found cooler outdoor temperatures corresponded to higher CO2 concentrations within classrooms. And we believe this is due to the reduced likelihood of opening windows or vents during cooler periods. And that really highlights the challenges faced with balancing, say, occupant comfort and ample ventilation in our classrooms. And this is found throughout the day as well, so temperatures are often cooler in the morning when a building's getting up to temperature. And that often corresponded to higher CO2 concentrations and peaks being kind of observed mostly in the mornings. So as I said earlier, CO2 isn't the be all and end all of classroom air quality, but it is a good indicator of ventilation performance. And, good ventilation prevents, the buildup of harmful pollutants. So moving on then to PM 2.5. Again, it's another super important pollutant, and especially in classrooms. And it poses a significant health risk alone, by itself. It accounts for almost, I think, 60, maybe even more, 66, 67% of typical indoor, the harm kind of from indoor air pollutants is just PM 2.5. And the World Health Organization has guidelines. So the 24-hour guideline value for PM 2.5 is 15 micrograms per cubic meter. And we actually found that this 24-hour guideline value was exceeded on almost half of monitoring days within classrooms or in the study. And further investigation by utilising the EPA's outdoor air quality monitoring network in the country, we found a strong positive kind of correlation between outdoor PM 2.5 monitoring stations and classroom PM 2.5. Suggesting, I suppose, that ingress is one of the dominant factors, influencing classroom PM concentrations. And we found PM 2.5 isn't a problem that's exclusive to cities or urban areas, but it's more rural schools too are facing this kind of challenge of dealing with ingress of outdoor PM. Additionally, then we found some strong inter and intraday variations in PM. And we can see that strong diurnal pattern in the graph, as well as the similarity between indoor and outdoor concentrations. And classroom PM 2.5 concentrations were also quite often elevated on cold days, cool, still days outside. And we feel, elevated outdoor PM 2.5 and its impact on classroom air quality is an area that doesn't receive a whole pile of attention, but does merit some consideration in naturally ventilated schools. This graph here then also highlights that it's not just an outdoor source, that indoor sources can also, contribute to PM levels, high PM levels within classrooms. So there you can see a candle lighting event is causing a spike in PM concentrations. And similarly, something like sweeping or physical activity within the classroom could cause resuspension. And again, PM 2.5, given that the majority of the sources do seem to be outdoors, it's a good example of where, low CO2 concentrations doesn't necessarily equate to good overall indoor air quality. So we could have a low CO2 reading because lots of fresh air is coming in, but if that air from outside has plenty of particulates in it, it's might be a bit misleading, that low CO2 figure. On a more positive note, though, our nitrogen dioxide levels are quite a bit lower than what's been reported in previous studies globally in schools. But our formaldehyde is a little bit higher, and I think what's interesting is spread. There's a kind of a significant variation within schools So I think that's quite an interesting finding. And then with limonene, we're actually quite a bit lower than the European mean there as well, which is somewhat positive. So I guess some of the key take homes here from my little talk is that classroom air quality really does extend beyond carbon dioxide, and I really want to hammer home the importance and impact of occupant behavior and appreciation and knowledge of indoor air quality and the role that it plays in ensuring healthy environments, I suppose, healthy classroom environments. And ventilation absolutely can reduce the buildup of indoor generated pollutants, but it does present an avenue for outdoor pollutants to enter a classroom. And we're hoping with the retrofits and the MVHR units being introduced and the filtration within them, it should help to some degree to address this. Other things that's worth considering and can help improve classroom air quality is, careful consideration of the cleaning products that are used, furnishings and floorings. All of this can go a long way towards improving classroom air quality. And finally, just to mention that the post-retrofit measurements are well underway, and we'll be looking forward to sharing those with you guys once they've concluded. So Sinead, thank you very much.
Thanks very much, Adam. That's great. Really good to hear about the classrooms and the impact, especially for our youngest citizens, and looking forward to hearing the further results once you have the measurements done post-retrofit. Thanks. Our next speaker is James McGrath, who is an assistant professor at Maynooth University and member of Icarus Climate Research Centre and Kathleen Lonsdale Institute for Human Health Research. James's research activities include fundamental and applied research in the field of indoor built environment, where he focuses on indoor environmental quality, aerosol science, and building ventilation. James's recent work has focused on assessing climate change adaptation measures and implications for large-scale national retrofit. He currently serves on the International Society of Indoor Air Quality and Climate and their board of directors, and is the Irish representative on the Air Infiltration and Ventilation Centre board. So now, James, it's over to you when you have your slides ready. Thanks.
So thank you very much, Magda. So I suppose I just kind of want to start off by thinking more of a big picture. And I've said this was a picture I took when I was up in the middle of the Swiss Alps about 2 years ago. And it was the idea of clean, pristine air. And the idea would be that that's the expectation for all the indoor air quality indoors, and particularly in schools. But the reality is that's often not the case. So if I just move on, if we think about the school environment, then it's really the idea to, I suppose, where learning is focused, but often other activities can particularly take place. And it's the idea of, particularly in primary schools, there can be a lot of arts and crafts taking place. There can be various levels of small exercise. You could have lunch indoors, particularly on stormy or rainy days, but then candles or incense or other activities can actually be used, particularly with children for special needs, that can be used kind of to relax them and create more of a soothing environment. So I suppose we have to think of a classroom beyond just, I suppose, students sitting down looking at a board. And it can be harder to adapt to all of these, I suppose, multifunctional requirements. And I suppose briefly, just to kind of reiterate what Orla had said. So I suppose when we look at the EPBD, there is, I suppose, this requirements now to, I suppose, start to consider the broader indoor environmental quality, which includes the temperature, humidity, ventilation, and the presence of other contaminants, with the reference of human health. But we really kind of need to think about this is really set out more for ensuring minimum requirements and regulations. And particularly if we often look, we see the word adequate, or sometimes it's inadequate. But I think really we need to be looking beyond that. Like if I hear adequate, if somebody told me they went to a restaurant and was adequate, I wouldn't be really keen to kind of go back. Or if the children turn around and the teacher said their performance was adequate, as a parent, you'd be kind of slightly concerned. You'd want to be doing better. I think we should be striving to do better, particularly with the indoor environmental quality in these environments. So just, I suppose, when we think, I suppose, of some of the current challenges associated with schools, there's various different requirements and aspects we need to be considering. Some are very much the climate targets and, I suppose, the decarbonisation, energy performance with it. But I think we're also now in an era where we can't no longer be just looking on mitigation measures. We unfortunately need to start looking at adaptation measures as well. And like we know our climates are getting warmer due to the buildup of CO2. So we need to start building our schools not just to meet the the mitigation requirements, but also adaptation, while also kind of realizing that these are kind of spaces for learning and prioritizing the health and comfort with multifunctional environments. And particularly then there's this aspect of schools have kind of an occupancy of primary schools will say 9 to 3, secondary schools are 9 to 4. So they're very different occupancy schedules compared to maybe other larger offices and buildings, and particularly the residential environment. And we need to consider these factors in as we're developing them. So if we just look at some of the broad evidence to date from a very much an international perspective, we can really see that a healthy environment, and particularly the indoor air quality and environmental quality, is really linked with student absenteeism. We also see when the environmental quality improves, the test scores improve and student learning improves. And we can see ratios of between 3 to 6% increases depending on the studies that we're looking at. Again, Adam touched on this, but really the cohort of students that we're looking at, particularly in primary schools, are smaller. So the air to volume ratios, or the air to mass rate, sorry, I should say, the inhalation to mass ratios are significantly higher compared to adults. But in a global sense, really a lot of the schools around the world are very much focused on the idea of natural ventilation, which to date haven't been meeting the needs of these schools. And particularly, I suppose, we just need to have a slight element of caution when we talk about natural ventilation, because in some elements it's purpose provided, so it's intentionally designed to meet those requirements. In other international contexts, it can be much more infiltration. So the building is, I suppose, if you want to call it, leaky enough, or it's dependent on windows and doors to be open. And I suppose an interesting aspect is particularly pupils definitely feel more comfortable in a colder environment than an adult environment. And then it begs the question of, well, who are we trying to design the building for, but who has control of that building as well? Just to build again on what Adam said, the influences of outdoor air quality, if you just look at a recent study completed last year in the UK, they were actually finding that 9 out of 10 of the schools that they looked newly constructed schools were actually exceeding the WHO guidelines for PM, I think it was PM 2.5. If we look at some of the broader existing challenges internationally, and particularly evidence from the US, which has gone to a lot more of mechanical ventilation, particularly some of them that have cooling aspects, they've typically reported evidence where a lot of times if the systems are turned off because they're too noisy, they're interfering with the teaching. There's broad aspects then of the systems not being maintained properly. There was about a 50%, I suppose, failure of inspection. So when they were checked for either maintenance or filters or the flow rates, that there were over half them were failing. Then there was the other aspects that the systems were typically only used to provide heating and cooling, as opposed to actual appropriate ventilation and renewal of air. And then again, I suppose that's the idea is that they can often be used, I suppose, in a measure to reduce energy costs, but that they're not always then utilized in the correct manner to achieve the end target. So if we look at some of the broader challenges in terms of energy retrofit, and we know we're trying to retrofit the entire building stock, schools and offices are no exception. Adam has already touched on some of the specific targets, but we need to start to be kind of looking at very much the climate adaptation measures as well as the mitigation measures. And one study that was recently conducted in the UK, again, they actually they proposed the idea of including what they referred to as a cognitive performance loss. So how would the school children impacted, or their ability to learn impacted as a consequence of these mitigation measures? And they actually found the schools where energy retrofitting was taking place, particularly, I suppose, measures to insulate the external envelope, were actually having a negative impact on their cognitive performance. But what they actually found was some of the passive climate adaptation measures, which were actually having a benefit in terms of the daytime ventilation rates, were seen to mitigate some of the changes of climate change. If we just consider this in the specific then in the context of Ireland, in terms of the energy retrofits, and Adam has touched on this in terms of the residential stock, we have seen issues where energy retrofitting does lead to negative impacts on indoor air quality. there's always this balance of trying to maintain energy performance versus the indoor air quality aspects, particularly if the ventilation isn't given due consideration as part of the retrofit. But we also need to be mindful of this one size doesn't fit all, and we do need to be able to tailor our approach depending on the environment and the location that we're dealing with. And particularly then again, as Adam touched on, is this balance of indoor and outdoor sources, depending on the pollutant sources that we're looking at, means we need to be mindful of different aspects. And then particularly then in Ireland, radon is a specific challenge. We've seen this from residential studies, but it's also been extensively reported in kind of the schools. So in Ireland, all the schools were measured back in the late 90s. So I suppose we need to be mindful of when those mitigations were put in place, that we're not, how the energy retrofit is going to impact these aspects. But I suppose one of the interesting studies that's kind of come out of Paul O'Sullivan's group in MTU was they actually looked at the aspects of thermal resilience and the idea of what can be referred to as passive cooling or ventilative cooling, which is the idea of natural ventilation. And they actually found that natural ventilation had certain aspects to be able to address the variability to be able to maintain an indoor air quality when we have varying outdoor air temperatures. And in particular, that it was now able to adjust to the risks of overheating due to the changing climates. So we continue on and consider, as we're developing broader indoor environmental quality management strategies, there's some broad aspects that we need to consider, and some of these have already been kind of touched on. But really, we would always say the first way to address indoor air pollution is to try and remove it at source. So if we talk about radon, is to have appropriate radon mitigation measures in place. If we're talking about VOCs, it's essentially to try go for low emitting VOCs materials, and it can be to remove any of the specific sources then that are generating specific pollutants. If we talk about humidity, and again, this has already been mentioned, but really localized extraction is a key priority. And particularly if we talk about this, really, I suppose in schools, it's kind of the bathroom areas, particularly now as they seem to be moving more within, I suppose, a classroom environment as opposed to broader kind of centralized facilities. So I suppose odor and other aspects then can start to become an issue that we need to be mindful of. Particularly then there's controlled substances, whether it's candles, incense, obviously cooking less so, but depending on the environment and the scale of the school, at secondary school levels, there could still be centralized cooking facilities. Ventilation, then we need to be mindful of the flow rates, the extraction rates, and particularly filtration. Monitoring, we need to be kind of conscious of the CO2 measures associated with them, but also, as Adam has highlighted, we need to be able to go beyond CO2 and look at the broader indoor air quality metrics. And then we need to be mindful of the operational maintenance and particularly filters that are used with these systems. So if we were to just, briefly look at some of the pros and cons of different ventilation strategies, we talked briefly about natural ventilation. It's very cost effective. It's sustainable. There's a very low carbon footprint associated with the design of it. So if we talk about the life cycle assessment of buildings, occupants can typically engage with it. They're quite comfortable with opening a window. It's opportunities for passive cooling, and there's not a lot of maintenance associated with it. But then some of the downsides, there's variable flow rates, we have limited control, it can have drafts, there can be security issues depending on the environment. But then I suppose there's no filtration associated. We can't control the infiltration of outdoor air indoors. We look at this with the advantage then of more mechanical systems. We can particularly get a constant flow rate, which could be required for higher occupancy. It can have advantages for energy efficiency, but again, we need to be mindful of this, particularly in the duration of the occupancy and the operational periods that we're considering. It does have the advantages of filtration, which I mentioned, but some of the downsides, and we've seen this from residential studies, but even the studies in the US, there can be failures in the system that people don't know about that can result in faults. Noise can be a particular issue, but then the long-term maintenance is something that's a particular challenge then as well. And if we just touch on the health and safety code of practice, which Orla had mentioned, we can see within these, it's quite useful that there is these kind of CO2 standards now that can be referred to it. The UK has similar values. There's the 1000 ppm, which comes from ASHRAE, which Adam mentioned. But I think we just also need to be mindful of, if we're dealing with a classroom of 5-year-olds versus a classroom of 17-year-olds, the exhalation of the CO2 rate is going to vary because of their metabolic rate. So while these CO2s are very useful, we also just need to be able to ensure we use them within the proper context. There's some advantages then. If we talk about the filtration, we can use filters to be able to clean and remove some of particularly the particulate pollutants, but it can also be used for some of the chemical and biological. But we just need to be mindful of a lot of the standard MERV filters, particularly internationally used, are around the 7 to 8 kind of MERV rating, which wouldn't capture the particles that, I suppose, Adam has presented in some of his research. So we really need to ensure that if we're looking at filtration as an avenue, we also need to be ensuring that the appropriate filters are going in and that they're maintained. But unfortunately, the issue becomes even more complex when we kind of look at the broader avenues. So one aspect of work that was done that was led by colleagues in DTU in Denmark was looking at the idea of the tail, which referred to the thermal, the acoustic environments, the indoor air quality, and the visual environments. I should say there's work, Asit is actually doing work to kind of renovate this, particularly in the context of schools. And what we can do is we can use this method to assess some of the interdependencies and the broader, if I want to use the word, holistic views to capture what's going on. But some of the challenges can be that, for example, the thermal comfort can impact the indoor air quality. And we've seen this from Adam's work, where the outdoor temperature will impact how often people want to open the windows. We've seen then, particularly if we look at acoustics and light can have an impact on both the thermal environment, but also, I suppose, the generation of ozone indoors. Again, acoustics and thermal can have different interrelationships between outdoor noise and infiltration. And then the thermal aspect can be influenced by the lighting, particularly if there's large windows, you can get increased temperatures. And then similarly, we've seen that the acoustics can actually impact the air quality, where people are turning off ventilation systems because of noise. So there's quite an interrelationship between these factors that we need to consider. And the idea of the CO2 monitoring has been used, so I won't really dwell on it. But I think what we just need to be trying to consider is, if we think of buildings very much have kind of energy standards associated with them from an international perspective, and some of these are starting to include the broader indoor air quality metrics. But if we think about schools now have kind of the Green Flag Award for the likes of recycling, for, I suppose, kind of sustainable initiatives, but we shouldn't really be looking towards a certification where we can actually say, yes, this is a broad, healthy school. One of the challenges with these things, and why they've been used quite extensively over COVID, is really trying to kind of keep that, maintaining the engagement. And particularly with teachers, there was an element of fatigue that crept in. So there was kind of a struggle to keep engagement with these. Just lastly, to touch on one of the projects that, and again, Adam is the PhD student on one of these projects. I'm still involved in this project. But one of the aspects that we're also looking at is trying to look at newly constructed energy efficient buildings to engage with the broader aspects. So Adam is looking at the pre-post retrofit. We have a postdoc in Galway looking at the newly constructed buildings and to see how to compare. And we still have a few places left to recruit schools. So if anyone knows of any of them that might be interested, please do feel free to reach out to us. If you just Google Benefit University of Galway, you'll be able to find it. And I suppose just lastly, to summarize, I'm probably running short on time, is really as we move ahead, we have particular challenges that we need to be mindful of, new regulations, but also trying to hit our energy efficiency targets. Overheating and cooling strategies are something we now, unfortunately, probably need to be mindful of, particularly as we start to kind of feel the impacts of climate change. And at what stages, if we're going towards mechanical ventilation, do we need to start considering installing cooling mechanisms associated with them? And then particularly if we're talking about schools at a primary level, even secondary level, we need to be kind of mindful of the maintenance and the management of these systems. Particularly, a lot of this is usually done locally. And we would have seen evidence with this with radon, where strategies we were put in place, but by changing of staff, retiring of caretakers, principals, that knowledge didn't necessarily transfer throughout the staff cohort. So I suppose that needs to be also ingrained. And we just then need to kind of, the ideas particularly of new pollutants that are emerging, we need to be constantly able to adapt and change. And unfortunately, there is potential, the risks of future pandemics in the future. Climate change is having impacts on the longevity and the longevity of viruses, particularly normal colds and flus. And we need to just be mindful of the infection risks, that we need to be able to develop schools that are able to adapt to these as well in the future. And thank you very much.
Thanks very much, James. It's great to see the amount of research that is published on the topic, and also really nice to see that Ireland is very well, and Irish researchers are very well represented using Irish schools and dwellings as case studies. So that's brilliant to know, because it all helps developing the policy and guidelines for schools and building owners how to operate those.